Oh, happy Pi Day, everyone. It's that wonderful time of year where we celebrate the greatness of the circle constant. I even bought this nice shirt at the joint math meetings in January to celebrate. I'd wear it more often, but I got pi all over it. Anyway, today on Scholar Sauce, we're going to consider the concept of pi and explore a few geometries where pi masquerades as a number other than the usual 3.14159, etc. Hey, while you're here, subscribe to Scholar Sauce and let me know in the comments how many digits of pi you have memorized. The number that we denote with the Greek letter pi comes from the fact in Euclidean geometry that if you take any circle's circumference and divide by the length of its diameter, you'll always get the same constant number, that 3.1415925 number from before. But what if I told you that there are geometries out there where this ratio is still constant, but it equals a different number? To understand how that's possible, we have to explore a little of how we calculate the number pi in Euclidean geometry. The calculation of pi is inseparably connected with how we measure distance in Euclidean geometry, which is governed by the Pythagorean theorem. This says that for a right triangle in Euclidean geometry, with leg lengths a and b and hypotenuse length c, we have that a squared plus b squared equals c squared. Now consider a vector v equals xy in R2. That is an arrow pointing from the origin to the point xy in the xy plane. We can apply the Pythagorean theorem to define the length of this vector as follows. The length of the vector v is equal to the square root of x squared plus y squared. That is, the vector length is the hypotenuse of a right triangle formed by the vector and its horizontal and vertical coordinate lengths. We call this vector length a norm. No, not that kind of norm. This distance function allows us to define the circle of radius r in R2 in terms of it. Namely, the circle is equal to all the vectors v in R2, where the norm of v is equal to r, or all the points xy in the xy plane, where the square root of x squared plus y squared equals r, which looks like this graphically. It's just a typical circle. Now we know the circumference of this circle is going to be 2 pi r, but in order to be able to deal with this with the other kinds of geometries, we need to know a little bit about how we calculate that. We can use the norm that we just found to compute the circumference of the circle by using a little calculus. We will compute the circumference by calculating the arc length around the circle. This is done by integrating the arc length. For those unfamiliar with calculus, essentially what we're going to do is add up the lengths of an infinite number of infinitesimally small straight line segments that make up the circle. To do this, we first need a parametric function for the circle. Given the equation of the circle, x squared plus y squared equals r squared, we can solve for y and get that y is equal to plus or minus the square root of r squared minus x squared. To compute the circumference, we really only need to compute the arc length of the quarter of the circle that's in the first quadrant, and then we can multiply it by 4 to get the entire circumference. Thus, we only need the positive version of this equation. This yields the parametrization of this quarter circle as gamma of t is equal to t square root of r squared minus t squared, where t comes from the intervals 0 to r. The derivative of this curve is the tangent vector of that curve at every point, and it can be calculated as gamma prime of t is equal to 1 and negative t over the square root of r squared minus t squared. Then we can compute the arc length by integrating the norm of this tangent vector along the curve. And you can use calculus from there in order to find that this is equal to pi over 2 times r. And hence the circumference of the circle is c is equal to 4 times the integral from 0 to r of the norm of a gamma prime of t dt, which will equal 4 times that pi halves r, or just 2 pi r, as expected. Dividing this by the diameter, or twice the radius, yields that c over 2r, which is equal to 2 pi r over 2r, which will be equal to pi, or that familiar number 3.14159265358, and so on. And that's what we expected to get for the value of the ratio of a circle's circumference to its diameter. But now, let's apply this same idea to other kinds of geometry to see if that ratio changes. It's so good. Oh, sorry. One way to talk about a different type of geometry is to change how we measure distance. Now, we can't just pick any random notion of distance. We need to somehow pick something that actually behaves like distance. And looking at the Euclidean distance function, we can kind of get an idea of what those properties ought to be and make this a little more precise. The three most important properties that the Euclidean distance norm has are the following. For all real numbers s and vectors u and v in the xy plane, we get that 1, the norm of s times u is equal to the absolute value of s times the norm of u. 2, the norm of u plus v is less than or equal to the norm of u plus the norm of v. This is the triangle inequality, or another way to say that the shortest distance between 2 points is a line. And third, the norm of u has to be greater than or equal to 0 for all vectors u, and it equals 0 if and only if that vector happens to be actually 0. Well, it turns out that there are a lot of functions that satisfy these three properties. For example, one way of measuring distance is the way a taxicab taxi might in a city with a gridded road system like New York City or Salt Lake City. A taxi has to travel on the roads and can't go in a straight line in any direction, but only in the horizontal and vertical directions. Thus, the length of the vector v equals xy in the xy plane, if it had to drive like a taxi, would have to be the norm of v given a taxi metric equals the absolute value of x plus the absolute value of y, how much it moved horizontally plus how much it moved vertically. And that's because the taxi has to traverse both the x direction and y direction to get wherever it's going. This function, though, satisfies all three of the important properties that the Euclidean norms satisfy, and hence has similar behavior. This justifies its consideration as a type of length measure. Well, now we could ask what the circle is given this length measure, and in that case, the circle of radius r about a point would be all the points in the city that are exactly a distance r away using the taxicab's odometer. And that is, the circle of radius r would be this set here. The circle given the taxicab metric is equal to the vectors in the xy plane where the norm of the vector v given the taxicab metric is equal to r, which is the set of all points xy in the xy plane where the absolute value of x plus the absolute value of y is equal to r. Plotting this circle yields an interesting shape. The circle in this metric is this diamond or rotated square. This geometry not only has a new notion of distance, but a new notion of circle, and consequently it turns out a new notion of the value of pi. To compute the circumference, we have to use the same norm that defined the circle, and this is going to require us to use a similar integration technique to what we just did with the Euclidean norm. We'll also again just compute the arc length in the first quadrant, that first quarter circle, and multiply the result by 4 in order to get the entire circumference. In this case, the quarter circle in the first quadrant satisfies the equation x plus y equals r, or y equals r minus x, and hence a parameterization of this quarter circle is gamma of t equals t r minus t, where t comes from the interval 0 to r. Thus, the circumference given the taxicab metric is c sub taxi equals 4 times the integral 0 to r of the norm of gamma prime of t with respect to the taxicab metric, dt, which is equal to 8r. And dividing by the diameter 2r yields that the pi in the taxicab norm is pi sub taxi, which equals 8r over 2r, which is just the number 4. That is, in the taxicab metric, pi is sort of LARPing as the number 4, or 4 is LARPing as the number pi, whichever way makes the metaphor make sense to you.
LARPing stands for live action role playing.
This has to make you wonder whether there are different geometries where pi takes on even more different values. And indeed, there are many. Let's investigate a little further to see a similarity between the two norms that we've already considered, see if there's something there that we can exploit to create even more norms. And don't mind me. The Euclidean norm follows the formula for a vector v in the xy plane, norm of v equals the square root of x squared plus y squared. But you can write this another way. It's the quantity, the absolute value of x squared plus the absolute value of y squared, quantity to the 1/2 power. The taxicab norm, on the other hand, follows the formula, the norm given the taxicab metric is equal to the absolute value of x plus the absolute value of y, which we can also write another way as the quantity, the absolute value of x to the power of 1, plus the absolute value of y to the first power, the whole quantity raised to the 1 over 1 power. Notice that these two now kind of follow the same pattern, just that the exponents on the x and y and the denominator, the fractional exponent, change. To keep track of that, we'll call the taxicab norm the L1 norm, and the Euclidean norm the L2 norm, to indicate that their power was 1 and the denominator there was 1 for the taxicab metric and 2 for the regular Euclidean one. But this suggests that there are norms for other values of this number, and indeed such norms exist, and they're called the LP norms, and they're defined precisely as you would expect for a vector in the xy plane. Here, the norm of that vector given the LP norm will be equal to the quantity, the absolute value of x to the p power, plus the absolute value of y to the p power, all raised to the 1 over p power. Now, the next thing we have to check is whether or not these actually satisfy all the properties that we said needed to be a norm. And it turns out that this function does indeed satisfy all those same 3 properties that the Euclidean norm satisfied, as long as p is a real number that's greater than or equal to 1. The geometries associated with these norms are called the LP spaces. The circle of radius r can be defined for each of these norms as follows. The circle given the LP norm is equal to the vectors in the xy plane where the norm of v given the LP norm is equal to r. Or it's the set of points xy in the xy plane where the quantity absolute value of x to the p power plus absolute value of y to the p power, all quantity to the 1 over p power, is equal to r. Now let's plot what these circles look like for various values of p. Note that the circle starts out as the taxicab diamond we saw earlier for L1, and then for p values between 1 and 2, it kind of grows until it becomes the Euclidean circle, once we get to L2. And then it continues to progressively change and become more and more boxy, with the edges getting flatter and the corners sharper as p increases. This might make you wonder what would happen to this circle if we let p go to infinity. In fact, you can actually show that the limit as p goes to infinity of the quantity absolute value of x to the p power plus the absolute value of y to the p power, all quantity to the 1 over p power, will actually just equal the max between the absolute value of x and the absolute value of y. And hence we'll use this to define what we'll call the L infinity norm for a vector v in the xy plane. That is, the norm of v with respect to the L infinity norm is just the max of the absolute value of x and the absolute value of y. And in that case, the circle of radius r in the L infinity space is simply the circle, given the L infinity norm, of vectors v in the xy plane, where the norm of v with the L infinity norm is equal to r. Or, in other words, every point xy in the xy plane where the max of absolute value of x and absolute value of y is equal to r, which looks like this, which is yet another square. And you can see how the circles in the LP spaces limit to this as p goes to infinity. Now that we know what all these weird spaces look like, we can go ahead and start calculating the value of pi in each of these spaces. The value of this pi, by the way, is blueberry, but that's not really what I meant. Since we have to compute the circumference using the same norm that defined the circle, we're going to have to continue to use that integration method that we were using before. But again, we'll be able to just calculate the arc length in the first quadrant and multiply it by 4 in order to get the circumference all the way around. Also, to make things easier, because these integrals are going to get a lot worse, we're going to go ahead and set the radius to just be 1, so that we'll be talking about the unit circle. Since the value of pi doesn't depend upon the value of the radius, we'll be able to get the value we want this way while doing a simpler computation. The first quadrant quarter unit circle in any of the LP spaces will satisfy the equation x to the p plus y to the p equals 1, or y equals the quantity 1 minus x to the p, all raised to the 1 over p power. This means that a parametrization of this quarter circle is gamma of t equals t, and then the quantity 1 minus t to the p to the 1 over p power, where t comes from the intervals 0 to 1. And hence the circumference of this circle will be c sub p, which is equal to the integral from 0 to 1 of the norm of gamma prime of t with respect to the LP norm dt. But from there, pi in the LP norm is just this value, cp, divided by the diameter, which the diameter in the unit circle is just 2, and thus pi sub p is going to be equal to cp divided by 2. And this works for any real number p greater than or equal to 1. Here's a list of some of the values pi sub p for some different values of p, as well as a graph of the values of pi sub p against the value of p. And we can also calculate the value of pi infinity. To do so, it follows the same pattern, but it requires some mildly tricky piecewise functions, but it can be done with just some algebra rather than calculus if one wanted to. Nevertheless, the value of pi infinity, like pi sub 1, is just 4. And so this graph, if taken out to infinity, would limit to 4. Now notice that the minimum value of pi sub p appears to be the value of pi sub 2, which is just the Euclidean norm, and our most familiar value of pi, 3.141592653588979. Yeah, that one. A couple of neat observations about the value of pi in these metrics is that just as it appears from this graph, the value of pi sub p satisfies the inequality pi is less than or equal to pi sub p less than or equal to 4, where pi equals 3.14159265358979323 as usual. Moreover, you might have noticed that some of the values of pi were the same for different values of p. And it turns out that pi sub p will equal pi sub q if and only if 1 over p plus 1 over q is equal to 1. Those that are more familiar with the LP spaces will know that the LQ norm, where p and q are related like this, is called the dual norm to LP, and hence the value of pi is the same for an LP norm and its dual. But there's actually a little more that we can say here. It turns out that there are even more potential norms and distance functions that can be imposed on the xy plane. And given any possible distance measure on the xy plane, it's been shown that the value of pi in that distance measure has to be a number between 3 and 4. And in fact, for any number between 3 and 4, you can find a distance measure on the xy plane that'll produce that number as pi. But if one assumes that the distance function that you're using will produce a unit circle that has quarter turn symmetry, then again the value of pi given that distance measure will be between the Euclidean value of pi, 3.141592653589793233846. Whew! Between that number and 4, just like it was for the LP norms. So the big takeaway here is that if we don't want to exclude any potential distance measures, then really every single moment in the month of March is Pi Day for some distance measure. That is, we really ought to be celebrating Pi month in March and gorging ourselves on pi all month long. Well, thanks for watching Scholar Sauce. on this fine Pi Day. If you want a couple of more fun Pi Day videos, you can check out my video from last year on how the Bible seems to have gotten pi wrong, or the video from the year before that where it suggests that you should stop saying that pi is infinite. I've also collected a playlist of all my Pi Day videos here. Be sure to like this video and subscribe to Scholar Sauce, and wish Albert Einstein a happy birthday, and we'll see you next time on Scholar Sauce.